Okay, so today's study assignment, which I think is F, if I'm not mistaken. It's all about balancing redox reactions. We talked about in class during that chapter sort of really basic balancing of redox reactions where you really just need to make sure that the electrons are the same. But in these type of reactions in acidic or basic conditions, it does take a little bit more steps along the way to balance those type of redox reactions, which we will talk about here right now. So a reminder that redox reactions does mean obviously oxidation and reduction. And we talked about several definitions of these, but the ones we mainly focus in on here is the loss of electrons when something is going through oxidation, and the gaining of electrons when somebody is going through reduction. Some alternate sort of definitions of oxidation is the gaining of oxygen as you go from reactants to products, or the losing of hydrogen as you go from reactants to products. As I talked about sort of in lecture, you know, if you get into organic chemistry, you really do kind of use those definitions a little bit more than the others. And also the opposite is true for a reduction. It would be the loss of oxygen from reactants to products, or the gaining of hydrogen as you go from reactants to products. But really for us in here, it really is sort of the electrons that we do follow. And as we talked about, you know, you could do the oil rig, you could do Leo the Lion Goes Grr, and you could also help you figure this out by following our oxidation states, right? So our oxidation states are numbers, and we really talked about the rules for that. So just to highlight some of the main ways of assigning oxidation states that we talked about, remember that anything sort of in its uncombined state by itself will have an oxidation number of 0. If it is just an ion that's by itself, whatever the ion's charge is the oxidation number on that, if it's a monoatomic ion. Things like group 1 and such have their normal sort of charge as their oxidation numbers. Oxygen, which is usually a really good place to start with, has an oxidation state of -2. The only time it would not be -2 is if it was peroxide, which it would be -1. And remember that when we sort of, hydrogen is +1, except when it comes after a metal, it's -1. And when we do add up all the oxidation states in a compound, it should equal the charge on it. So if it's neutral, all your oxidation numbers should add up to 0. If it does have a charge, then obviously it should add up to that charge. The other important thing is, as when you are sort of citing oxidation numbers, you should include the charge. So if it's +1, you should write +1. You know, if it's -2, you should write -2. So you should include the charges when you're doing that. We also talked about that certain things, our elements will obtain an oxidation state different than what we sort of think about for particular elements, especially in ionic compounds, is sort of what we always sort of think about the charges on everybody is when they form an ionic compound. But in a covalent bonding situation, as we talked about the other day, by sharing electrons, and depending on who they're sharing with, they can take on very, very different charges or oxidation states really than their charges we associate with ionic compounds. So again, something like chlorine, for example, we usually associate as being -1, but it definitely can take on like a +5, +7, a much different sort of oxidation state. So the oxidation state in a covalently bonded thing will be a little bit different what we see with the ionic. But if you do have an ionic compound, then it will really be the same as the charge we normally associate sort of with it. Remember that you could also just kind of follow a number line if you're not sure what's happening. And when you do lose electrons, you do become more positive. So if you find the oxidation state is moving kind of to the right here, that means that thing is going through oxidation. And obviously, if somebody is gaining electrons, they're going to become more negative. So if you see the oxidation state kind of moving towards the negative direction, it would be going through reduction. Now, this is also not to be confused with a couple other important terms that we talked about, which is the oxidizing agent and the reducing agent. So the oxidizing agent, again, is the substance that gets reduced. So when it gets reduced, it means it wants to gain electrons. So the only way for it to gain electrons is to have somebody else lose electrons. So it causes somebody else to lose electrons. And the reducing agent is the substance that gets oxidized. And same idea, when this guy gets oxidized, he's going to lose electrons. That's going to cause somebody else to gain the electrons and go through reduction. So they cause the opposite effect, obviously, in the other substance. Now, other important things that we talked about, which will be helpful in what we're going to be talking about here in a second, is the idea of half reactions. And for a redox reaction, remember that if somebody is going through oxidation, somebody else has to go through reduction, and vice versa. If somebody's going through reduction, somebody else is going through oxidation. They always happen together. And the nice thing about that is if you're able to just identify one of them, by default, the other guy has got to be doing the opposite thing. So, you only have to really identify one thing, what's being oxidized, what's being reduced. And by default, you can figure out really the other, what's happening to the other substance. But we do write half reactions, and the half reactions are really either the oxidation half reaction or the reduction half reaction. So, if we had something like silver goes to silver plus an electron, this would be a oxidation half reaction. This is silver going from an oxidation state of 0 to +1. And if we again follow the number line there, it is obviously starting at 0, going to +1. So it is being oxidized. And we know that because in the oxidation half reaction, the electron should always be on the product side. So that is definitely, what should happen. Electron should always be on the product side in the oxidation half reaction. Now that's different than if we had maybe something like this. This, we have the electrons on the reactant side, and this is chlorine in its natural state, which is 0, and chloride, which is -1. So once again, if you do the little number line type thing, chlorine is starting at 0, ending at -1, going more negative, going through reduction. This would be the reduction half reaction. And we know that because the electrons should always be on the reactant side. So reduction half reaction, electrons should be on the reactant side like they're being gained. Oxidation half reaction, electrons should be on the product side like they're being given off. They're again called half reactions because we could add these guys back together to get the overall reaction that is happening in this particular case. And if we do that, I'll just rewrite them on the next page or not. We'll do this. I'll go here. So we had on this one here, silver going to silver plus an electron, and then we had a couple of electrons plus some chlorine going to 2 chlorides. So once again, oxidation and reduction half reaction. When we have sort of a simple redox reactions like this, and we have the 2 half reactions, when we go to add them together, the one thing that we always have to make sure of is the electrons here are the same number. And that's because when somebody gets oxidized, however many electrons they lose, it's the exact same amount of electrons that somebody picks up as they're going through reduction. So in this case, we do actually have to multiply the top half reaction by 2 to get us the same number of electrons. And I'll write it right underneath. So we'll have 2 silvers goes to 2 silvers with the plus and a couple of electrons. At this point, what we could do is add both of these reactions together. And when we add both of these reactions together, basically anybody who's on the left-hand side of the arrow stays on the left, everybody on the right-hand side stays on the right-hand side. And you can reduce it down now if you want, or you could just bring everybody down and do it at the end. So I'll just wait to the end here and just bring everybody down. So 2 electrons plus some chlorine plus a couple of silvers, right-hand side, 2 chlorides plus a couple of silvers there, and our 2 electrons. Now, you could think of the arrow kind of like an equal sign in math. So you could subtract the electrons from both sides and they will cancel out completely. And if you do this correctly, they should always cancel out completely. If you do it incorrectly, they will not. Also, if you end up with electrons on the same side of the arrow, you definitely screwed up somewhere. So they should never, ever be on the same side of the arrow. They should always be on opposite sides of the arrow. And when you add them together, they always need to completely cancel out. What we end up with is the overall reaction here that is happening. And this would be the balanced redox reaction here. And when we balance redox reactions, they need to be balanced really in two ways. They need to be balanced like a normal equation, which means you need to have the same number of elements on both sides. So we have 2 chlorines on the left, 2 on the right. We have 2 silvers on the left and 2 on the right. So it's balanced like a normal equation. The other thing that needs to be balanced is the overall charge on both sides of the arrow. They need to equal each other. They do not have to equal 0 on both sides, but whatever charge you have on the left, it should be the exact same charge you have on the right. If we look on the overall charge on the left-hand side, chlorine has no charge. Silver, which is a solid, has no charge. Overall charge on the left is 0. Overall charge on the right, that chloride has a -1 and there's 2 of them, so that's -2. This silver has a +1 and there's 2 of those, +2. +2 and -2 gives you an overall charge of 0 on the right-hand side. So it is balanced in terms of the charge on both sides. Overall charge on the right is 0. Overall charge on the left is 0. And that is exactly what you always want when you're balancing redox reactions. So that's a really good way to check yourself when you're all done. If you're adding everything up on both sides, you got different numbers of elements, that's definitely not balanced. And if the overall charge on both sides is not exactly the same to each other, then it is not balanced either. So that's really the two things you want to make sure an equation should be. And once again, it does not have to be 0 on both sides in terms of charge, but just doesn't need to be the equal number. So if this happened to be +2 and +2, you'd be good, whatever it may be. So this is sort of a simple redox reaction here that you would balance. Any questions on any of those sort of steps? By the way, the oxidizing agent here would be which thing? The oxidizing agent would be this guy. Yes, that is the guy being reduced. The reducing agent would be that guy there, right? That is the guy going through oxidation. So again, those are the two things that you sometimes are asked as well. Okay, so you may come across some of these basic sort of ones to balance and really just get the electrons the same and you're good to go. Now, when we do balance redox reactions in either acidic or basic conditions, there's a lot more steps that you have to sort of follow to sort of balance these reactions. And that's what we're going to talk about next, which is how to go through those steps. So we'll go through one here together, show you how to do it. All right, so let's say we took this guy here and this was a redox reaction that we wanted to balance. And again here, it is not balanced. If we just look at the overall charge on the left, that is +2 and -2, that's 0. Overall charge here on the right is +3 and +3, which is +6. So that definitely is not balanced on each side. So although it may be balanced in terms of elements, which it is not either, it's not balanced in terms of elements. So this is definitely not a balanced equation. We're going to first balance this guy in acidic conditions. So we're going to do this guy first in acidic conditions. So the first thing that we want to do really is separate out this reaction into the 2 half reactions. So we want to separate it out into its reduction and oxidation reaction. So even if you are not sure what's going on in terms of which one is which, the very easy way to separate these guys out is the guys have the same element. So iron goes with iron, chromium goes with chromium, and those would give you your 2 half reactions. But let's take a second here first to try to figure out what is happening in terms of who's being oxidized and who's being reduced. Iron over here has a +2 oxidation state since it's an ion by itself. We did this guy the other day. The chromium ended up with, anybody remember? This oxygen is -2, so that's -14. -2 overall. The chromium here ends up being +6 on the left-hand side in terms of its oxidation number. I think that was on one of the examples we did. So it's -14, and you have 2 of them, gets you +12, gives you -2 overall. On the right-hand side here, the iron is +3, and on the right-hand side, the chromium is +3. Now, in terms of the iron, is it going through oxidation or reduction in this case? It is going through oxidation. Again, if you're not sure, the iron started at +2, which would be here, and going to +3, which would be going to the right-hand side there, going through oxidation. By default, that means that this guy is going through reduction, but we could see that as well. If you just do the little guy here, chromium started at +6, which is over here, ended at +3, which is going in this direction, becoming more negative and going through reduction in that case. Any questions on how to identify that there? That also means that the iron is our reducing agent, and the dichromate here is our oxidizing agent in this case. All right, so now that we have that all sorted out, which technically speaking, you might not have to do, but it's good to know so that as you do the process here, you know if you kind of screwed up or not. So what we're going to do is take this and separate them out into 2 half reactions. So we're going to start with the iron 2 going to the iron 3. So those 2 guys are obviously related to each other. The other one we're going to do is the dichromate going to the chromium. Those 2 obviously have chromium in there, so they are related to each other. All right, so the first thing you want to do is separate those guys out into their half reactions. The next thing that you want to do is, so you want to separate half reaction. The next thing you want to do is balance all elements except hydrogen and oxygen. So all elements except hydrogen and oxygen you want to balance. So when we look at the first half reaction, there's 1 iron on the left and 1 on the right, so we're good. On the bottom one, there are 2 chromiums on the left, but only 1 chromium on the right. So we want to balance it just like we would do a normal equation. We're just going to put a 2 in front of it. And again, that will take care of the chromium. So all elements other than oxygen, hydrogen, we're going to balance just like normal, put a coefficient in front until we have it there. At this point, it is time to balance the oxygen. The way that we balance oxygen here is to balance the oxygen, we add water to the side that needs the oxygen. Now, when we add water, we are adding oxygen, obviously, but the other element that's in water is hydrogen. So because we're adding water to one side, we need to add H plus to the other side. So to the other side, we'll get 2 H pluses for every water you add. And that is just to make sure at the end, you're not short hydrogen. So if you just add the water, not the H pluses, at the end, when you go to balance, you're short some hydrogens and stuff like that. By the way, if you ever start out in a situation like this, where you have more hydrogens on one side than the other, you would add H pluses, equal number to the other side, just to balance it out. So sometimes you may have, like, say, HNO3 on one side, NO2 on the other side. You have an H to start with, more on one side than the other. You would add H plus to the other side to balance it out. All right, so we're going to balance the oxygens now. And what we're going to do is look at the top one. And obviously there is no oxygen in the iron, so we don't have to worry about it. When we look at the second equation there, there's 7 oxygens on the left and no oxygens on the right, which means the right-hand side will need 7 waters to balance out the oxygens. Because we added 7 waters to the other side, we need to add 14 H pluses to take care of the hydrogens we added. 7 times 2 is 14, is basically. So we're going to add 14 H pluses to this side. Any questions on that? So water is added to the side that needs the oxygen to balance it out. opposite side of water, you need to add H plus so you're not short hydrogens in the end. 2 H pluses for every water that you add, basically. Any questions up to there? Okay. At this point, we're actually ready to balance everything in terms of charge on each side. We balance all the elements. We've added our water to balance our oxygens and hydrogens. We're now going to balance the overall charge. So what I'm going to do is, I know getting too low is too bad, so I'm just going to rewrite it on the next slide here. So we have Fe2 plus to Fe3 plus. We did 14 hydrogens plus some dichromate. And that was chromium 3, which had a 2. And we did 7 waters, I believe. See how I did there. Looks good, I think. Okay. All right, so what we're going to do now is balance the overall charge on each side. So the next step that you want to do is actually add electrons. So we're going to add electrons to balance out the charge. On each side of the arrow. Since electrons are negatively charged, we need to add to whichever side needs the negative charge. So looking at the top equation, on the left-hand side, it is +2. Right-hand side, it is +3. The side that needs electrons is the guy on the right. It actually needs 1 electron. By adding the 1 electron to the right-hand side, that's +3 and -1, which gives you +2 on the right. Left-hand side +2, so we're balanced in terms of the charge on both sides. Now, personally, the best thing to do in this situation is to look at the overall charge. Some people get so focused in on, I want to look at all the individual oxidation numbers, and you really don't need to do that. When we look at something, for example, like dichromate over there, the -2 overall is the sum of all the oxidation numbers of everybody. So we could just go -2 and +14 is a +12 sort of happening on this side. On the right-hand side, that is +6, and 0 is +6. So in this case, the overall charge is +12 and +6. That means the left-hand side needs the electrons, the negatively charged, and they should need about 6 of them, I believe. That now gives me a -6, which gives me a +6 on the left and a +6 on the right. We are balanced now in terms of overall charge. Any questions on that there? This is one place where you could stop for a moment, since we did the very beginning part there, and we could check to see if we screwed up or not, in a sense, because we already determined that the iron was going through oxidation, which means the electrons should end up on the product side, which they did. And we decided that this guy is going through reduction, which means the electrons should end up on the reactant side, which they did as well. So again, by doing that step at the beginning, you should know which side should get the electrons, and that is what we see here. Any questions so far? The next thing we're going to do is actually just add these two together, but just like we talked about with the basic redox reaction, we cannot add them together until both electrons are the same. So the bottom guy's got 6 electrons, the top guy's only got 1. So we do need to multiply the top reaction by 6. And again, you're multiplying everybody by 6 there. So I'm just going to kind of clean up this a little bit here. A little bit more too. Here. So if we do that, I'm just going to kind of copy it underneath here. We will end up with 6 of the iron 2, 6 of the iron 3, and 6 electrons. Again, we'll clean it up a little bit more here. At this point, we have both half reactions that we can add back together. At this point, and we see, like we expect, electrons on opposite sides of the arrow and the exact same amount. And again, you could cancel at this point if you like. Anything that's on opposite sides is the same. You could cancel out or reduce down. So the electrons should completely cancel. And I think in this case, that is all that will cancel. So what we're left with is everybody on the left-hand side of the arrow stays there. Everybody on the right-hand side stays there. So that gives us an overall of 14 H pluses plus a Cr2O72 minus plus a 6 of the iron 2 goes to 2 of the Cr3 plus 7 waters and 6 of the Fe3 plus here. Get that out of the way. And 3 plus. Now, if I did everything correctly, this should be balanced in acidic conditions, and it should be balanced the exact same way that we talked about, like a normal equation. We should have the same elements on both sides, numbers. That's 14 hydrogens there, 14 there, 2 chromiums, 2 chromiums, 7 oxygens there, 7 there, 6 irons, and 6 irons. So we're balanced in terms of elements. Overall charge on the left-hand side, that is plus 14 here, and a minus 2 is a plus 12, and a plus 12 again is a plus 24 overall charge on the left-hand side. Right-hand side, that's a plus 6, that's a 0, and that's a plus 18. That's a lot of math, but I'm hoping that's plus 24 on that side as well. And we are balanced in terms of overall charge on the left and right and elements. And this would be balanced in acidic conditions. Any questions on any of those steps there? So break off into half reactions, balance all elements other than oxygen and hydrogen. Then balance oxygen by adding water to one side, H plus to the other side. Add electrons at the end there to balance out the overall charge on each side. Make sure each half reaction has the same number of electrons, then add them together. And this would be balanced in acidic conditions. How do I know it's acidic conditions, by the way? I know it's acidic conditions because it has an H plus right about there. H plus is basically generic for an acid. So if you see an H plus in your final equation, that's like acidic conditions that you balanced it in. Any questions on that there? Okay. Now, you can also have to balance these equations in basic conditions. And there's a couple different ways you can do it, but the easiest way to do it is pretty much to do what we just did, which is basically balance it in acidic conditions. So even if it tells you to balance it in basic conditions, you should follow all the exact same steps we just did, balance it in acidic conditions. And then at the end here, you can kind of turn your acidic equation into a basic equation. So let's talk about how you do that. I'm just gonna, I think, recopy it on the next page here, so it's up higher. Maybe 14H plus is there. I'll go here. Not that. Okay, so we had there 14H pluses, right? And the 2, chromium and iron. We had this plus this plus this plus I think it was this plus mega memory here. There we go. 7 waters, not bad. 7 waters. There we go. All right. So this is our equation that we just did, balanced in acidic conditions, if I copied it correctly, I hope. Now we're going to turn it into basic conditions, and to turn this into basic conditions, what we're going to do is add OH minus to both sides equal to the number of H pluses we have. So to turn this guy into a basic equation, we're going to look at our equation and figure out how much H pluses we have, which is 14. And we're going to add 14 OH minuses to both sides, not just one, but to both sides in this case. So we're going to add on the left-hand side here, I'll squeeze it in, hopefully 14 OH minuses And on the right-hand side, I'll squeeze it in underneath, 14 OH minuses. So we're going to add 14 OH minuses. OH minus is basic, really. It's a hydroxide to both sides. Now, when you do this to the side where you have H plus and OH minus, when you have H plus and OH minus, that is our good friend water is going to be made. So on the side where you have H plus and OH minus, that will then give you 14 waters. And I'll just rewrite everything and keep everything here. A little bit of room. All right, so waters and our 14 OH minuses. Okay. Now, what usually happens in this case is you will have water on both sides. So as you can see here, I have 7 waters on this side, and I have 14 waters on this side. So again, you can treat the arrow like an equal sign. You're going to subtract 7 waters to the other side. So when you subtract 7 waters, that goes away. This guy now becomes 7 waters on the left-hand side, plus our chromium, plus our iron. And if we did this correctly, this would be the balance equation in basic conditions. And it should still be balanced the exact same way in terms of elements and charges. So if we look really quick, left-hand side, 14 hydrogens on the right. We have 7 oxygens in the first guy, 7 in the second is 14 oxygens, 2 chromiums, 6 irons. Overall charge on the left-hand side, that is 0, that is -2, that is +12, that is a +10, if I'm not mistaken. Right-hand side, that is a +18, that is a +6, which is a lot of math there. That's a +24, and that's a -14, and that should also be a +10, I hope, in that particular case. And we are balanced on both sides in terms of charge and element. I know this is basic because when I look in the final equation there, I see our good friend hydroxide. Yeah, basic. So it is hydroxide, unlike the acid one that had H plus, which is for an acid and stuff like that. Question on the steps. So basic, really the easiest way to do it is to just wait to the end, balance it like it's in acidic conditions, then kind of turn it into a basic at the end. The other approach is, if you ever look around, is sometimes you could add the water before you add the electrons, and that works out as well. But the problem with that is, if you're not really experienced or do it a lot, you have a lot of reducing down, you have a lot of waters right in the middle, and it kind of get confusing. So the safest approach is to just do it at the end. Anything else about reducing a whole bunch of stuff down in the middle of the problem and stuff like that. Any questions on balancing these type of guys here? A little bit more complicated than, get the electrons together and put them together. All right, so I did one, why don't you do one? Why don't we do this guy in basic conditions, see what you come up with. So in addition, figure out who's being oxidized, who's being reduced. Also figure out the oxidizing agent, reducing agent, and we'll balance this guy in basic conditions. So see what you come up with.